Hi everyone, this is a presentation on the paper entitled Zero-Shot Transfer with Deictic Object-Oriented Representation in Reinforcement Learning. Consider the following Sokoban task with 6 state space variables. In model-based reinforcement learning, we learn a model of the transition dynamics through interacting with the environment. However, if we try to do this naively, we run into certain challenges. Firstly, as the size of the state space or action space grows, this becomes intractable. Secondly, from a transferability perspective, if we have previously learned a model for the 6 state space variable task, and we now have this new 8 state space variable task, then it's not clear how we can transfer the model to this new task. One idea that's been suggested in the literature to overcome these challenges is the notion of object-oriented representations, where the aim is to learn conjunctions over logical statements that map to effects over object attributes. For example, we might learn that whenever the agent takes the action east, and there's a person with a wall object 1 square east of it, then that person's x attribute does not change. Two things to note. Firstly, the rule that was just described is a transferable rule, so it's true for any Sokoban task. Secondly, if we can compactly represent the transition dynamics of a domain with a small set of such rules, then we can get away from the large state space problem that was previously described. Previous work on object-oriented representations introduced a fully propositional framework. Under such a framework, if you wish to have a compact representation, then you must restrict your logical statements so that they do not refer to any grounded objects. However, such a restriction can be very limiting. For example, consider the 2 states depicted below. While it's true that in both states we have a box object with a person object 1 square west of it, and a box object with a wall object 1 square east of it, in the second state, these terms are true for different box objects, and this creates ambiguity over which effect occurs for a specific box. In the work presented here, the authors introduced the notion of deictic ONDPs, and the key idea is to allow for the grounding of the reference object for which we are trying to predict the effect. Therefore, we can ground the box object adjacent to the person and remove the ambiguity that previously existed. In this work, the authors formally define deictic OMDPs. They extend the Dormax algorithm of propositional OMDPs to deictic OMDPs, and they run experiments on the taxi and Sokoban domains, and show that as you add more objects, while under a propositional approach, you get intractable solutions, under the deictic approach you get tractable solutions. And furthermore, once you learn from enough source tasks, you can zero-shot transfer the transition dynamics to a new target task. Thank you for your attention, and for more information, please refer to the paper.